Here is something that will sound completely counterintuitive if you have been following the AI hardware race. The biggest bottleneck in running large language models right now is not compute. It is not the number of GPUs you have. It is memory. Specifically, it is a data structure called the KV cache. And if you are running any kind of production LLM system, it is almost certainly the thing that is quietly eating your budget, throttling your throughput, and limiting how many users you can actually serve. I am Mo, and this is the Practical AI Digest. Today we are talking about KV cache compression, the memory wall that nobody in the industry wants to have an honest conversation about, and two recent breakthroughs that might actually change the game. Let me set the stage with a number that should make you uncomfortable. A single instance of a large language model processing 100,000 tokens of context can consume 40 gigabytes of GPU memory just for the KV cache alone. That is roughly half the high bandwidth memory on an enterprise-grade GPU like the A100. Not the model weights, not the activations, just the cache of keys and values that the attention mechanism needs to look back at previous tokens. And that is for one user, one request. Now multiply that by the number of concurrent users you need to serve, and you start to understand why inference costs are where they are. The reason this happens goes back to how transformers work at a fundamental level. Every time a model generates a new token, it needs to attend to all the previous tokens in the sequence. The naive approach would be to recompute the attention for every single previous token on every generation step, which would be catastrophically expensive. So instead, we cache the key and value projections from each layer for each token and reuse them. That is the KV cache. It is a brilliant optimization that makes autoregressive generation tractable, but it comes with a cost that scales linearly with sequence length, linearly with the number of layers, and linearly with the hidden dimension. For a 70 billion parameter model with 80 layers, you are looking at about a megabyte per token per layer. At 100,000 tokens, that is 8 gigabytes per layer times 80 layers. The math gets ugly fast. This is what infrastructure people call the memory wall, and it is not a theoretical concern. WEK published an analysis in April 2026, framing this as the defining infrastructure challenge of the current AI generation. Their argument is sharp and I think correct. Organizations have been throwing GPUs at the inference problem, but GPUs do not solve a memory bandwidth bottleneck. You can have all the floating point operations per second in the world, and if your attention mechanism is waiting on memory reads from a bloated KV cache, you are memory bound. The GPU cores are sitting idle, waiting for data, and you are paying for that idle time at GPU prices. The practical impact hits in three ways. Throughput goes down because you can fit fewer concurrent requests in memory. Latency goes up because memory access patterns get less cache-friendly as the KV cache grows. And cost goes up because you need more GPUs not for compute, but for memory. This is why a company serving a chatbot to 1 million users is not spending most of its inference budget on matrix multiplications. It is spending it on storing and fetching the conversational context for each user. And there is a compounding dynamic that makes this worse over time. As models get larger and context windows get longer, the KV cache grows in both dimensions simultaneously. A model with twice the layers and twice the context window has 4 times the KV cache. Meanwhile, GPU memory has been growing linearly, roughly doubling every 2 to 3 years. The KV cache is growing quadratically, while the hardware is growing linearly. That is the definition of a wall. There is also a subtlety here that gets lost in the benchmarks. The memory wall does not just affect peak memory. It affects memory bandwidth utilization. Modern GPUs like the H100 have enormous compute throughput, over a petaflop of FP8, but their memory bandwidth tops out around 3 terabytes per second. When your attention mechanism has to read a 40 gigabyte KV cache for every single generated token, you are doing 40 gigabytes times the number of attention heads of memory reads per token. At 3 terabytes per second, that is over 13 milliseconds per token just for memory access. For comparison, the actual matrix multiplications take a fraction of that. The model is literally waiting for data, not crunching numbers. This is why you see companies like Grok building custom chips with massive on-chip RAM, why Cerebra's has their wafer-scale approach, and why even NVIDIA's Blackwell architecture prioritizes memory bandwidth over raw flops. The industry has figured out that compute is abundant. Memory is scarce, and the KV cache is where that scarcity hurts the most. So what do you actually do about it? The field has been working on this hard, and 2025 and early 2026 have produced some genuinely promising approaches. I want to walk through two of them in detail because they represent fundamentally different strategies. And understanding why they work tells you something important about where inference optimization is heading. The first is KVTC, which stands for KV Cache Transform Coding. This was published at ICLR 2026, and it takes an approach borrowed from signal processing, specifically from how we compress images and video. The insight is elegant. The raw key and value vectors in the KV cache have significant statistical redundancy. Adjacent tokens tend to produce similar key vectors because the underlying representations change gradually. Different attention heads within the same layer often encode partially overlapping information, and the distribution of values across the hidden dimension is highly non-uniform, with some dimensions carrying much more information than others. KVTC exploits all three of these redundancies in a pipeline. First, it applies PCA-based feature decorrelation to remove the cross-dimension correlations. This is essentially rotating the coordinate system so that each dimension is as independent as possible, which is exactly what transform coding does in JPEG and video codecs. Then it applies adaptive quantization, allocating more bits to high variance dimensions and fewer bits to low variance ones. And finally, it runs entropy coding on the quantized values to squeeze out the remaining statistical redundancy. The results are striking. On standard reasoning benchmarks, KVTC achieves up to 20 times compression with negligible accuracy loss. On some specific workloads, it hits 40 times or higher. And critically, it is training free. You do not need to fine-tune the model. You do not need calibration data. You apply it at inference time and it works. The compression and decompression are fast enough that the time spent compressing is more than offset by the memory bandwidth you save on cache reads. 20 times compression on a 40 gigabyte KV cache means you are down to 2 gigabytes. That changes the economics of inference entirely. You could serve 10 times as many concurrent users on the same hardware, or you could extend your context window by an order of magnitude without adding GPUs. There is a nuance in the KVTC approach that I think is underappreciated. The PCA rotation step is not a one-size-fits-all transformation. The authors compute the principal components per layer and per attention head because different layers encode fundamentally different kinds of information. Early layers tend to capture syntactic and positional patterns where the key vectors cluster tightly. Middle layers handle semantic composition where the variance is distributed more evenly. Late layers handle task-specific reasoning where a few dimensions dominate. By adapting the transform per layer, KVTC avoids the common trap of compression methods that work well on average but blow up on the layers that matter most for accuracy. The entropy coding step is also worth a closer look. After quantization, the distribution of quantized values is highly non-uniform. Some quantization bins are hit far more often than others, and that non-uniformity is free compression if you exploit it. KVTC uses arithmetic coding, the same family of algorithms that powers modern video codecs like H.265, to squeeze out this remaining redundancy. The overhead of the coding itself is negligible because the decoder runs on the GPU's tensor cores during the attention computation. You are effectively getting free compression from statistical structure that was always there, but nobody was bothering to exploit. One more thing about KVTC that surprised me. The authors show that their compression actually improves cache locality in some cases. The compressed cache entries are smaller, which means more of them fit in the GPU's L2 cache during the attention pass. This creates a virtuous cycle where compression reduces memory footprint, which improves cache hit rates, which reduces memory bandwidth pressure, which speeds up the attention computation beyond what the raw compression ratio would predict. The measured speedup is sometimes higher than the compression ratio alone would explain, and this locality effect is why. The second breakthrough is TurboQuant from Google Research, also at ICLR 2026. TurboQuant takes a different approach. Instead of the full transform coding pipeline, it focuses specifically on quantization, but does it in a mathematically novel way that eliminates the accuracy penalties that previous quantization methods suffered from. The key innovation is a technique called PolarQuant. Traditional quantization methods need to store per block normalization constants, scaling factors that map the quantized integers back to the original floating point range. These constants take up space and introduce error at the boundaries between blocks. PolarQuant eliminates them entirely by representing values in polar coordinates where the magnitude and angle can be quantized independently with tighter bounds. It sounds like a small change, but it removes an entire class of quantization artifacts. On top of PolarQuant, TurboQuant adds something called quantized Johnson-Lindenstrauss, or QJL. This is a dimensionality reduction technique that projects the key vectors into a lower dimensional space while preserving the relative distances between them, which is what the attention mechanism actually cares about. The Johnson-Lindenstrauss lemma guarantees that random projections preserve distances with high probability, and TurboQuant shows that you can quantize the projected vectors to very low bit widths without violating this guarantee. The combined result is 3 bits per element in the KV cache. That is a 6 times memory reduction. On NVIDIA H100 GPUs, the attention computation itself gets up to 8 times faster because the compressed cache fits better in the GPU's on-chip memory hierarchy. And here's the part that made me sit up. Zero measurable accuracy degradation. Not small degradation. Not acceptable degradation. Zero on long bench, on needle and haystack tests, on standard reasoning benchmarks. No calibration data required. No fine-tuning. You apply it at inference time and it just works. Now, you might be wondering how Google validated the zero degradation claim, because that sounds too good to be true. And honestly, when I first read it, I was skeptical too. But the key is in how attention actually works. The attention mechanism computes dot products between query vectors and key vectors, then uses those scores to weight the value vectors. What matters for the output is not the exact values of the keys, but the relative ordering of the dot product scores. If your compression preserves the ranking, the argmax, the softmax distribution, then the output is functionally identical. PolarQuant and QJL are designed specifically to preserve these relative distances, and the empirical results confirm that the preserved ordering translates to preserved output quality across a wide range of tasks. There is also a practical consideration that the paper addresses. What happens at the boundaries? When you compress mid-sequence, do you get artifacts at the transition between compressed and uncompressed cache entries? TurboQuant handles this by compressing the entire cache uniformly, so there are no boundary effects. Every entry gets the same treatment, which means the compression is invisible to the model. I want to be clear about why this matters beyond the obvious memory savings. The memory wall is not just a cost problem. It is a capability ceiling. Today, the practical limit on context length for most production deployments is not the model's advertised context window. It is how much KV cache memory you can afford. A model that advertises a million token context window but requires a terabyte of KV cache memory at that length is not really a million token model for anyone running real workloads. KV cache compression directly translates into longer usable context at the same hardware cost. It also changes the calculus on model architecture. One of the reasons mixture of experts models are popular is that they reduce the per token compute cost, but they do not reduce the KV cache size because every token still needs full key and value projections across all layers. With aggressive KV cache compression, dense models become more competitive again because their main disadvantage, higher memory usage per token, gets compressed away. I also want to put this in an economic frame because the dollar amounts clarify the urgency in a way that technical metrics sometimes do not. A single H100 GPU costs roughly $30,000, or about $4 per hour on the major cloud providers. If your KV cache is consuming half the GPU memory, then half of that $4 per hour is going to storing context, not generating tokens. For a company running 100 GPUs for inference, that is $200 per hour, roughly $175,000 per month, just on KV cache memory. A 6 times compression from TurboQuant cuts that to under $30,000. A 20 times compression from KVTC cuts it to under $9,000. These are not theoretical savings. They are the difference between an inference deployment that is economically viable and one that is hemorrhaging money, and it compounds. When you free up GPU memory from KV cache, you can fit more concurrent requests per GPU, which means you need fewer GPUs for the same throughput. Fewer GPUs means less data center power, less cooling, fewer network switches, less operational overhead. The KV cache is the first domino. Compress it, and everything downstream gets cheaper. So what does the practitioner playbook look like if you are running inference in production today? Let me give you 5 concrete things. Benchmark your KV cache memory usage per request at your actual workload lengths, not the model's maximum context, your actual PIFTY and P99 context lengths. Most teams I have talked to do not know this number, and it is the single most important metric for capacity planning. Evaluate KVTC or TurboQuant on your specific model and workload. Both are training free and can be tested without modifying your model. KVTC gives higher compression ratios but with more computational overhead. TurboQuant gives lower compression but with faster decompression and zero accuracy risk. The right choice depends on whether you are memory bound or compute bound. If you are not ready for a compression library, start with the low-hanging fruit. Sliding window attention on your KV cache, where you only keep the most recent end tokens plus a few anchor tokens from the beginning. This is not as principled as the compression approaches, but it is trivial to implement and gets you meaningful memory savings for conversational workloads. Set up memory observability. You should be tracking KV cache size per request, peak memory usage per GPU, and the ratio of KV cache memory to total GPU memory utilization. If that ratio is above 50%, you are leaving throughput on the table. Plan for the convergence. Google's official TurboQuant implementation is expected in the second quarter of 2026, and the major inference frameworks, VLLM, TensorRT LLM, and the rest, will integrate these techniques within a release cycle or two. The teams that understand the memory wall now will be ready to deploy compression the day it ships in their stack. The teams that do not will be 6 months behind, paying 6 times more for memory than they need to. And do not sleep on the second-order effects. Once KV cache compression is standard, the entire model serving landscape shifts. Longer context windows become practical on smaller hardware. Edge deployment of large models becomes feasible. The cost per query drops enough that use cases that were previously uneconomical, real-time document analysis, always. On coding assistance with full repository context, persistent multi-turn agents that remember everything, all of those become commercially viable. The memory wall is not just a technical constraint. It is a capability gate, and we're about to open it. There is one more thing I want to address because I know some of you are thinking it. What about multi-query attention and grouped query attention? These are architectural changes that share key and value heads across multiple query heads, and they do reduce KV cache size. GQA with 8 groups instead of full multi-head attention cuts the KV cache by the number of query heads divided by the number of key value groups. Llama 3, Gemma 2, and most recent models use some form of this. But here is the thing. GQA is an architectural decision made at training time. You cannot retrofit it onto an existing model. And even with GQA, the KV cache still scales linearly with sequence length. At long enough context, you hit the wall again. The compression techniques I have been talking about, KVTC and TurboQuant, work on top of whatever attention architecture the model uses. They are complementary, not competing. A model with GQA plus TurboQuant gets the benefits of both. The memory wall is real, it is expensive, and it is solvable. The research is ahead of the production tooling right now, but that gap is closing fast. The most important thing you can do today is stop thinking about inference optimization as a compute problem and start thinking about it as a memory problem. Because the GPU is not your bottleneck, the KV cache is. That's the one for this episode. In Mo, this is the Practical AI Digest. If you got something out of this, send it to one person who'd actually use it. No subscribe campaign, no rating farm, just one person. See you on the next one.